been a while. Great to see all of you. You look happy. There's an air of happiness in the room, or maybe because you said it was a good luck shirt.
Yeah, you guys
Katie. Thanks,
yeah.
thanks, Katie. I appreciate it. Although I feel very out of it. I don't know about you. I'm feeling like I'm just. It's like I haven't done this in a while. So yes, I've forgotten what we were up to. So do you remember where we were? No, I actually remember where we were. Do you remember where we were? Actually, before we even say that, how's homework 3 going? It's going. Any questions that you might have? Anything I can help you with?
I just thought if you could use the correlational matrix, but then you said
it's harder. Yeah, we don't do that anymore.
Okay.
That's the reason for that is if you've got missing data, the correlation matrix is likely to be biased. Right. If you've got and it's just I don't know, it's just not the same.
What are we supposed to do if we have missing data?
Just ignore it. If you have all the data in the data file and just you treat it as like an R, it's an NA, then it works fine. It's in maximum likelihood. It just
so in my file, the code I used for missing was 255. Do I just leave it like that?
No, you got to make sure it's not. Yeah, okay.
So, but what should I mark it at? Like what should
NA. The R official code is NA, and the way you can do that when you read in your data, if you're reading in
NA to strings.
Yeah, are you reading it in as like a CSV?
Yeah.
Okay, so in R. Hang on a second here. Let me pull it up. So in R, when you do like a read.csv, one of the things that you can tell it as an option is this NA strings right here. So if you have like your first of all, your read.csv is probably how you're reading it in.
Yeah.
So if your file equals like data.csv. You can tell it NA strings, and then you can give it the name or the number of the thing. I think if it's just 255, it'd be like that, and then it automatically converts. And it has to be like it's a string, it's a quote thing, I think, if I'm not mistaken.
Thank you.
Yeah. So what you want to make sure is it's an R, official R designated as missing, because then what Levon will do is it will take it and convert it. So when it's doing a factor analysis, because it's multivariate normal, like it's got this big, for every item in the analysis, it's got like a mean vector and a covariance matrix and whatnot. If you've missed an item, it just shrinks the size of it amidst the missing parts. So it makes it work it's actually better that way than otherwise. But thank you for asking the question. Other questions? Yes. Let me hang on just 1 second here. Here we go. I think I pulled up our lecture. There it is. Hey, there it is. Okay. The predicted item response. What you're looking for is to take. Here, actually. Bring up notes. This one right here. I'm going to create a brand new note. So I'm talking to myself. I'm sorry. I'm sort of feeling like I'm losing it for today for some reason. So here we go. So the predicted item response. Apple Pencil is great, but I forget to always plug it in to make it work. So the predicted. Okay, so are you looking for just a predicted item response or the graph of them?
The graph.
Okay, so the graph, if you look in my example, grab that real quick. Let me just double check I'm doing the right thing. I'll grab it over here. This thing. And this thing here. Okay, in the example file online, let's take the real data one. At the bottom of the file, there's this graph. The way that you make the graph, I have a Where did I put those? There we go. I have a function I call CFA plots. So if you find that function in my code and copy it.
Yeah. So I used that function and I got two graphs and I don't know how to interpret that.
Okay. Oh, how to interpret them. Okay. So what you want to do is make sure that this is a really crude, rough check of checking that your CFA assumptions are staying in bounds. What you want to see is that, for plus or minus, several standard deviation around where the factor mean is, or in this case, the range of factor scores that you're telling people to have, you want to see that the predictive responses for them stay within what the range of your scale for each of the items happens to be. So if you have a 5-point Likert scale, you want to see if the predicted responses are in that range. If they're not, it's not the end of the world. In fact, usually they're not. But so in this case, with these data right here, you'll see there's a few kind of at the low end of the scale. We predict score responses that aren't possible. But that's all. It's not a really inferential graph.
And in that question, you also asked about linearity.
Yes.
How can we use this graph and talk about that?
The best way of looking at it is this: if the linear, so you have this linearity, the assumption of linearity of the line, if it exceeds the range, effectively you're saying linearity shouldn't be in place, because you want something to allow it to be within the right range, and the only way to do that is sort of what we're talking about now. It's this: we need kind of a bendy function of the factor score to do it. Yeah, bendy. That's what I got that from my wife. It's bendy. Non-linear. Does that sound better? Sorry, I'm trying to have like the blue collar psychometric to it here, right?
Sitting down telling me about Jacobians, and now you're telling me about bendy functions. I just don't know how to reconcile.
You know what? I think if you think of it this way, you have to have a diverse set of ways of explaining it, because everybody has a different way of learning things, and I'm trying to get back to where why am I asking this and what fits? So yeah, I say bendy because it's like, well, I know where that goes. Yes.
I'm just yanking you.
No, I like it. Actually, I love it when you guys tease me. I think that's the best. So I totally cool with it, right? I'm totally cool. Like the way I try to approach my job is, especially with students, is I try to treat you as colleagues, even though I know I have to assess you and I have to whatever. But like, as if I do my job well enough, eventually you will be my colleague, right? So yeah, like if I see Dr. Skorupski down the hall and I've got something to say, I'll pick on him, right? And he picks on me, right? And so, actually, true story. Side note: I went in. He's on the editorial board of the journal that I'm editing, and he provided the review. And I went into his class. He teaches right after this. I went into his class to go and say, "Hey, thanks for the review." And he wasn't there. And the students were like, "Oh, are you?" One of them's like, "Are you Templin? Oh, I've never met you." He rips on you all the time in class. And then and so I was like, oh, really? That's interesting. And so, yeah, I think then they sort of played it up like we were trying to. It's like, well, tell him this. And so we're trying to go back and forth. But anyway, Shada, you had a question.
So you said that because the predicted item responses, well, I guess I'm wondering exactly how you phrase that. So the factor loadings extend beyond like the allowable.
Well, no, it's the predicted response extends a lot beyond the allowable range. So the range of what the item can be.
Okay.
And and for these data, like I think Lisa picked these because these graphs look pretty good. These are but a lot of data, it's way out there. And again, it's not a one-to-one thing. There's not a mathematical derivation I can give you about why this graph works, but it's more just trying to give you the sense of what you're trying to do, trying to connect the model with the data, right? So your data should be, like on this graph, my data should be between 1 and 7, and I've got some scores where I'm predicting they should get less than 1. That doesn't seem to make a lot of sense.
What do you say anything after that when you say they extend beyond the allowable range?
It just doesn't seem plausible. Perhaps a CFA model shouldn't be used. Something along those lines. That's the only thing you can say. But I'd probably say that before I saw this graph. So, yeah.
So then I have another question. So for the data that I had, the model showed that actually splitting up to a 2-factor model did it better, but not well, just a little bit better.
Okay.
So in the example, you know, it was really clear that some of the items were because they were reverse coded.
Yeah.
Was forgiveness and not forgiveness.
Mm-hmm.
But that's not really clear with the items that I have, so I'm
It
just
won't be.
calling it like factor 1 and factor 2
Okay.
because I just don't
Yeah, well, it's harder. If you don't have a clear idea,
of why it's happening.
right? I almost say like take the items that are the negatively worded and put a second factor on them, but don't call it. Just basically call it some type of like negative, like the influence of a negatively worded factor. Does that
But
make
if
sense?
they're not negatively worded, like
Then it doesn't measure it. So think of it this way. We talked a little bit about this in class about how this also could have been done differently. What we could have done with this example is still say that all 6 items measured one factor, but that the negatively or the reverse coded ones had some additional factor that was influencing how people were responding. That factor had something to do with reading the word negative. So you could do that, for instance. You could take all of your items, and then wherever they're reverse coded, have a second factor that only loads onto those items that are reverse coded. And so that main factor still means what you mean it to be, which is whatever the name was before. But now this other factor is essentially like the effective negativity or the effective reverse coding. It's what we call a methods factor.
okay, I guess maybe I'm not understanding, but if
Mhm.
they aren't negatively worded though,
Right. So if they're not, then it doesn't get the second factor.
You can't do a second factor.
Oh, wait, sorry.
Nothing.
Are all the items, do you have any negatively worded items?
No.
Oh, I'm sorry. I
That's
thought you
not-
said you had
sorry.
some that were. I'm sorry.
no, none of them
Oh.
were negatively worded.
No wonder you're leaving me to look like you're crazy. No, got
I
it.
was like, I'm
No,
following you.
no. No. If you can't see that, what is this? How did you find the second factor? I'll ask you that.
So, I mean, I looked at the relationships between them,
Mm-hmm.
and that was kind of how I noticed that some of them grouped together
Okay.
They're
more than
negative or positive, right? I had the same problem.
yeah, or they were just like
The
Yeah. So I think if you can't name your factor, probably shouldn't do that. Right? You got to be able to describe what needs to be. And I think if you're in a case where you come up with this weird grouping, but you have no idea what it means, it's probably not a solution you want to stay with. The solution I'd probably pick would be take the items that seem to take a look at the residual covariance matrix or the normalized residual, and if an item shows up a lot, like
yeah.
maybe that just remove the item from the scale altogether. Just shrink the number of items that you have,
Okay.
and because the smaller, two things happen: you get a smaller scale, you have fewer degrees of freedom, so it's a little bit easier to get model fit. But it could be the case that the item just isn't working with the others. But ultimately, you want to come up with a scale that you can understand what the factor means. The factor 1, factor 2 is kind of an exercise we do if this was just a math class, but I want to make it something a little bit more relevant to you.
Okay.
And if you know these data and you can't tell me what the factors are,
Yeah.
yeah, imagine submitting that to a journal. Right?
And then maybe if you just remove one of them and it
Mhm.
improves it just a little bit,
Mm-hmm.
and that's pretty much the best you can do.
That's sometimes what you have to do.
Okay.
Yeah, I think more often than not, that's what if you're thinking of piloting a new scale, which is harder because usually you're using someone else's scale, right?
Yeah.
But if you're writing it from scratch, you should write a ton of items just to get a core that seem to work. But in this case, if it's someone else's scale, you sort of have to make it work for your sample, right? So, does that help?
Can I?
Oh, yeah. I had a question, but do you have an add-on? Because I can.
It's kind of related
Okay,
to
I'll
that.
get to you in just a moment. Yeah.
Okay.
Katie.
No, it's actually not that related. You go ahead.
Okay.
It's related to it.
Okay, then.
Questions. I tried to fit a one factor
Mm-hmm.
like for the data
Mm-hmm.
you sent me, and a couple of issues.
Mm-hmm.
Uh,
A lot of issues.
so there is many negatives. I looked.
Mhm.
After that, I went directly and looked at the normalized
Mhm.
residual, and there are a couple of values above 2,
Mm-hmm.
higher above, and there are many values like although they are under the threshold
Mhm.
2, they are negative.
Right.
So I went back to your
The slides, yeah.
Your slide as well as your HTM
Mm-hmm. Mm-hmm.
sheet.
Yeah, where I showed the covariance matrix. Yeah.
Yes. So you indicated that if I understood you correctly, you indicated that negatively like values normalized residuals should be inspected and maybe they can be put together to represent a factor.
Possibly, yes. Mm-hmm. Mm-hmm. But possibly also with, I mean, so yeah.
So what is my questions at this stage? Because there are a couple of values above 2.
Mm-hmm.
Should I put, because I'm concerned about, like, when you said that you challenged us to publish an article with like a scale of something and stuff.
That's right. Yeah. How do you fix it?
So
Yeah.
when we add covariance to the model, it's kind of the same thing that we are. It's not, we are not doing.
Right. Yeah.
So what is the appropriate like steps that we can?
What
should
I
remove it or?
Yeah. Well, the first step is this: to take a look at the items of the scale, and see if there's a correspondence of some of the big normalized residuals, now either positive or negative, with items. Like, and now again, it's not your scale and it's not your field, so it's harder to interpret. And for the record, since I sent you the data, I'll tell everybody what you're working on. Yaya has body dysmorphic disorder, a scale about trying to talk about how people might incorrectly perceive their body image about a certain body part, right? And it's a typical type of scale. You'll see 14 items, I think.
Yes.
And so again, this is not a field that I'm in, and not a field you may know more than I do about it. Probably do, because I know next to nothing. It wouldn't take much to exceed my knowledge of it. But the reality of it is, the first step is you should go to the items and see if there's a discernible pattern. Saying, okay, I've got item, like, I'm looking at this normalized residual matrix here, and let's just take the biggest number I see. I see a 6.5 right here. Right? It's positive, but it's just 6.5. I just take the biggest one. And what's up with item 2 and 4? Is there something about them that causes me to take note? All right, so I'm going to read item 2. I'm going to read item 4. Take a look. And then I'm going to go to the next highest one. In this case, it's item 2 and item 6. I'm going to read item 6 now and take a look and see if there's any similarity. In the case of these items, we found that there was this reverse coded thing going on, it seemed to look like. So I would actually go see if where are the reverse coded items in your scale. I don't know if there are any. I can't remember. But that's a first place to look to see, should I put in a factor that involves reverse coding? But after that, I actually prefer removing items to adding residual covariance. Right? So I look here, and if I were to do that, I would say, okay, which item would I want to remove? Well, it's not exactly obvious. But if I were to count up, for each item, the number of times it has a value bigger than 2 or smaller than -2. 1, 2, 3, 4 of the 5 items for item 1. 1, 2, 3, 4 for item 2. Item 3 has 1, 2. Item 4 has 1. And item 5 has 1, 2, 3. Right? So, or I guess that's item 6. However, anyway, I may have done it. May have just missed one. Anyway, the point is, I sort of count up the number of times an item's misfitting with another one, and I take a look at that item, and I say, okay, the one that has the most misfitting items with others. Again, this is another crude approximation, but I want to know what item seems to fit the worst. And I go look at that item and I see how is it worded. And sometimes the wording is suspect. And so, all right, well, maybe it's not being interpreted the way I think. I take the item off. So, does that, hang on. Yeah. Hmm?
Yeah. So, how many times is it okay to go through that cycle? Of like,
Until
you just keep, right? Okay.
Yeah.
I have 31 items.
Jeez,
right?
yeah.
And I initially was able to take out 6 right away.
Mhm.
Like, these don't account for a third of the variance. And then when I ran it again, there were 3 more that didn't.
Yep. Mm-hmm.
And then I started doing this, and I wondered.
Go on and
oh
on and
gosh,
on, yeah.
Is this a total waste of my time? But as long as I'm on the right track, I'll keep doing it.
No, that's exactly it. No, I think that's the hard part. You can take data. Sometimes you can take a scale and never make it fit, or you have to radically change it to make it fit. Right? And so sometimes, if you've got terrible fit, like terrible misfit, RMSEA of like 0.2 or 0.15, something that's really bad, and you take a look at there's all sorts, and you have 31 items, you don't know where to start. Sometimes it helps to start in the opposite direction. It's like, well, if I were to rebuild this scale, what are the items I'd put first? Right? And so, okay, let me go look for the items that are sort of central to what I think the scale should mean, from the items that I have.
Would you want to keep trying to add more in though, while still staying above that index of good model fit, so that you have better?
That's right, yeah. But again, that's also a hard process too. It's like, so yeah, it's not an easy task, and some of your data will be, you get it as good as you can. Describe for the homework, get it as good as you can. Describe the process.
Mine will look better now that I know what to do about
Yeah, that also will help. But no, I mean, basically that's yeah. Actually, if some of the items had more missing than others, that might actually cause some weird craziness with your results. But yeah, I think that's a hard part. I mean, there may be cases in your life where you'll never get a model to fit for your data. All right, it's just not going to work. There's some discrepancy between the data and the model, and sometimes that's the scale doesn't work the way it does. Maybe it's the sample. Maybe it's who knows what. Did I answer your question, Yaya?
Yes, but she mentioned
Or Shady, you had a
that
question.
she used the criteria of if the item has been accounted for. So 30% is the common.
No, I actually, I mean,
This is the
that was
question.
sort of what we did in the homework.
Yes.
You can use that, but that to me, I look at whether the factor loading is significant, right? So if you look at the factor loading,
Can you show us?
yeah. So here, under your latent variables in your output, I want to see whether those, if sometimes when you fit a scale, when you fit all your items into it, if the factor loading has a p-value that's really high, that tells me take that item out, because it's not measuring if the factor loading is not significant, then what you're saying is that number there is effectively 0, and if it's effectively 0, then that's not measuring the trait, so you can remove it from what you do. The 30% thing, sometimes it's just you have items like that. They're just not. So you can leave them on. You may not be. It's sort of a different standard. I know that fits more the 30%. R squared of 30% kind of fits in with what we used to think about with EFA 0.3, even though the 0.3 in EFA is more like an R squared of 0.10, 0.1 or 0.09. So it's a tough thing to really see. Shade.
So after a discussion about the negative and stuff, I went back and I looked at those items again,
Mm-hmm.
and they're not negatively worded, but not like they would need to be reverse coded.
Uh-huh.
But they do have. There's a difference between them. That's half of the items have to do with feeling good and like a good student, and the other one is if I don't do this then I feel bad.
Ah, so there's a clue, right? So that might be.
And that's consistent, and then it does support the model, the two-factor model structure that I found to be better representative of.
Then if you can kind of put a label to the factor and then describe it, that would be meaningful, definitely.
Okay.
Yeah.
Okay, because okay.
Yeah.
I think that would be better than. I tried to pull out one.
Right.
That made better, and it not really, but when I split it, then it really did. But now the theory supports.
That's cool. Yeah. The other thing I would mention the reverse coded. It's also true for items with the same stem. Like sometimes you'll have a scale where 10 of the items start with I feel like, I feel like, and then another 15 don't have that. Okay, so if it's worded very similarly, you might have to put something in to control for the wording of the item itself. So you're looking for sort of patterns that might try to describe it, and then so sort of when you put it, if you were to do this type of analysis, I'm sort of talking to everybody here. So if you do this analysis and you kind of get a weird result, and you're like, okay, so how do I do this? Those factors that you put in to kind of control for similarities, whether that be reverse coded or stem or something like that, we call those methods factors, right? They're nuisances. They're sort of they're getting in the way of measuring what you're really after, which is the factor of interest. And so you put them in the model. What they're going to end up doing is take information from the factor that you're interested in reporting, but that's going to give you a more accurate report of that factor itself by controlling for them, right? It's almost like we're doing like the latent variable version of a multivariate regression, because you put a variable in a regression model, you're kind of controlling for values of that. You're going to control for weirdness in wording. You're going to control for weirdness in the reverse coding. You're controlling for the types of things that show up in a survey that may get in the way of or influence a person's response more than just their factor. So
I'm sorry,
Yeah.
can I make sure one thing? So
Mhm.
just this example just happened to be negative
That's right.
wording.
Mhm.
Okay.
that's right. This happened to be negative,
For
but
negative.
there's all sorts of ways this can show up, right? There's
Okay.
the hardest part though is when you have I think this is where we had our slides. I don't know if I can pull the slides up or not. We had a ton of slides from that lecture, but some of the examples where we had here, I'm going to try though. Give me a moment, please. let's try lecture 2. I think it would be actually lecture 1, the very first lecture of class. At the very end of it, we had sort of examples of surveys that had different types of weird item things going on. Oh, that's new in PowerPoint. That's fantastic. Thanks. Can I just get to it? What's new? Hey, how about this? I'd like to work. Oh, shoot. Hang on. Forgot that PowerPoint won't open up in some area. Okay. Here we go. This is where you have like take a look at what's happening here. If you look at the items over here on this, it's just the DERs, yeah. You notice a trend? When I'm upset, when I'm upset, when I'm upset, when I'm upset, when I'm upset. There's a bunch of these items that talk about when I'm upset, and then all of a sudden you've got a few that are like, not when I'm upset, right? And so you've got an entire factor here, a lack of emotional clarity that doesn't have when I'm upset in it. But then you've got entire factors that have when I'm upset on everything. And then there's a factor over here that has reverse coded items for everything. So there's a lot of things that might be going on, trying to adjust how someone reads the item, thinks about themselves, and then circles a response or however they try to input their response.
So in the example, because they were negatively worded, it was like they were two different factors.
Right.
So
But you don't have to have them be different.
Right.
I'm sorry. Let me put it this way. Let me go to the example. Let me get into R4. And we're going to go with not simulate. We're going to go with the real one. I'm going to make a copy. Oops. Okay. Give me just a moment to run everything. And then I'm going to go down and I'm going to show you another example of what we could have done for it. So here, what did I call it? Model 03. Here we go. So here's Model 03, where I have one factor, Model 03 syntax. What does that look like? Of course. Here we go. Here's my Model 03 syntax. I have a factor here that's situational positivity. If I changed it, see, there's this one factor that loads on everything, right? If I change that to look like this, if I had the negative, if I sort of had a negative factor that had only just the negative items on it, then the items that were only negative would then have their own factor to them. So pardon me, those items that were negative would have two factors loading onto them. It's sort of controlling for the negativity to it. And in doing this, oftentimes we think of that negative or that nuisance factor. Sometimes we call that the methods factor as being unrelated to. Oh my goodness, unrelated to the original factor. So if I were to put a covariance in between the two of them, I might make that equal to 0. I don't want negate. I can't believe it's calling it negate. Excuse me. All right, here we go. Yeah, it's one of my pet peeves is technology. Even Lisa tells me, yeah, just don't get mad at your computer in front of your class. That probably won't go well. That's what happens. So if I did this, you'll see what I end up getting is really good model fit again, similarly, right? A great RMSEA. But now I've got a factor here that measures what I would call situational forgiveness, which is what my original topic was. And now I have a negativity, what we call a methods factor. And so when we write up this type of model, we'd say, yeah, to make the model fit, we had to control for the effect of the negative with the reverse coding. And so this negativity factor is not going to be something we report to the user, not something we report to our clients.
So why we it's so what's the contribution of this factor? It's not, if we have two factors, and the first one is the one that we gonna report, and the other one is not. So how is that the other one contribute to the first one?
The
We
other,
delete the items, and that's
what it's doing is it's essentially saying that the why these two items are correlated or covary is not just because of situational forgiveness, right? It's because of wording. And essentially, wording is a sort of a method of things. How we design the survey is getting in the way of us measuring the thing we're interested in, which is situational forgiveness. So,
what is it's unclear is that if you said that we will not report it
to the person who, if we're trying to give a score to a person, we wouldn't be giving them a score on negative, the impact of negativity on how they change their answers. Right? That's what that negative factor really represents. We would basically say,
but still, if we are going to publish this,
we would tell all about it. It would be all there in the text. We would say, because of the way this was, it appeared, and we talk about our model building process. We may even put the normalized residual matrix in and say we resolved it by saying we added this method factor for negatively worded items, and it made the model fit better. We know why the model wasn't fitting as much. Essentially, we add this factor and we can explain it with this. The impact of it, what it's going to do statistically, is that factor will effectively make it harder to measure the factor of interest. It's going to be a lower reliability for situational forgiveness because those items where you have the two loadings is sharing their information between the two factors. And if we look at the loadings for those items, and if we look at the standardized loadings, you'll see over here that those loadings are the situational forgiveness loading is actually standard in the standardized sense lower than the values of yeah, that's right, lower than the negative factor for it. So it's essentially saying that the coding, the reverse coding for it is almost affecting these items more than, like the way that we wrote that question is affecting it more than the actual trait that we're trying to measure underlying it. Yeah.
So how do you decide between the two ways? Like, should we split them up into two factors, positive and negative, or account for wording? I mean,
I've always accounted for wording. The fact that they're split up for both might be something where if you're really familiar with an area, maybe there are two different types of forgiveness, and you can explain why that would be. But for me, I don't work. My area is in quantitative methods, so I don't have a quantitative method scale. So I mean, the point of the matter is, I have a harder time describing why you'd want to split those into two unique factors that mean something than I have saying I'm going to control for the negative worded factor. Right?
so in this way, it would still be a one-factor model.
It's a two-factor model.
Two-factor, okay.
But the score of interest, the only score that you would report still would be to a person would be the situational forgiveness score,
Okay.
right? And so basically you've controlled for the impact of wording on each of those scores themselves.
Does that situational forgiveness score that you give the person incorporate their responses to the negatively worded items?
Yeah,
Or
it's
right?
controlling for
'Cause
it.
you're still keeping them.
That's
in the
right.
model.
That's right. So each person would have a negatively worded factor as well. Like we could even find it.
Right, but no one wants to know what their score on that.
And what does it actually mean? It's sort of a matter of understanding kind of how consistently, a high value on there says they're widely inconsistent from what the situational forgiveness would tell you when you get to those negative worded items, something like that.
so it seems that it's kind of like we are controlling the residual related. It's a kind of residual because if we add the second factor, the standardized values for the second factor with their corresponding value, it will sum to 1.
Yeah, I mean, it doesn't sum to 1. I mean, ultimately, like, no, it's no. I mean, ultimately, what we're doing is we're taking what normally would be part of the situational forgiveness, what we're interested in, and taking out the part that deals with how they read the negatively worded question. And so when we give them that situational forgiveness score, it's sort of now controlling for their ability or their way that they responded with the negativity or the negatively worded question, if that makes sense. I mean, ultimately, it's taking a part of the first factor and doing something with it. And yeah, we're not going to add them back together, though, because that part is a nuisance. It's sort of not related to the trait of interest, right?
But I mean, theoretically speaking, now if we add the two, it will sum to one.
No, not necessarily. No, there'll be all sorts of potential. I mean, summing to one. I mean, adding the two loadings themselves.
For example, if you go to the STD standard.
No, yeah, they're not, they look like they're summing up to one, but what's happening is they're summing up. It's what there is a dependency in that the squared loadings, the sum of the squared loadings plus the residual variance has to equal 1. Right? So because they just happen to be about the same, or just about the same size. It's just by chance in this case, right? And so what we're saying, the residual variance for each of these items is, it varies a little bit, but because of that, it's sort of what gives us, the sum of the squared loadings gives us the factor, the R squared also. I mean, that's another way of putting it. So for each of these items, but.
I'm sorry to keep asking.
No, it's okay.
So my items are a list of like just the one simple verb: eating, dressing, using toilet, sleeping, or napping.
Mhm.
Those are not negatively
No, not at all.
or anything. Then I shouldn't use the two-factor model.
It's harder to understand what it is unless those items align in a way that would become another factor.
Yeah, so I think that's why the example was just too perfect for.
Oh yeah,
for
yeah. The
me
example is,
to
and that's why it's an
misunderstand.
example. Yeah.
Yeah, that like because negative worded just came up like negative, and I mean anyway.
Yeah.
Yeah, so if it's too hard to, because I didn't create this assessment. If it's too hard to make it two-factor, then I should just use a deletion.
That's what I probably would do.
Okay. Okay.
Deletion, or if those are activities,
Yeah.
if there's a certain if you can group activities into different types, I don't know that you can, but
No, I don't. Yeah, I just don't
Yeah.
know. Yeah, what happened there? So yeah, it's just simple.
Or if one of these is not like the others, maybe you remove that item, something like that. So napping, I don't know if that's a. I don't know. Again, I'm not in your field, so I don't know
Yeah.
what.
No, I guess
Yeah.
that's all home life activities.
Yeah, they are. Yeah, they are. Well, I mean, not all home life activities are created equal. I think that's what I'm trying to say, right?
Yeah.
Like some take more effort or energy, and what do you? And so like, I mean, I've seen the similar type of thing with a scale for like functioning in older adults,
Mm-hmm.
and so can you toilet yourself? Can you? And like. Some activities are a lot more complex than others, and so it's almost like.
But that's subjective,
It
though.
well, it can be. Yeah, it's true.
That's why I'm afraid to do that.
That makes sense. Well, then don't.
Okay, then
This is good,
I just go
and
with
that's the rationale you have. There you have it. Go with that.
Oh, okay.
That's good. I'm not gonna be a journal editor when I review this. I'm gonna try to help you shape your argument,
Yeah,
but I'm not gonna try to
Okay.
rip it apart.
Okay.
Yeah. Could you close the door also, please? Sorry about that. I hear the whistling outside. I
Like
realize my.
music.
What's that? Yeah. Yeah. I know my voice also carries, so I feel bad for the people around it.
Okay, thank you.
Thank you. Is this helping some? Yeah. So again, yes, the example was perfect to sort of provide scaffolding for learning the material. Now the homework is not that, and that's why the homework is there, because reality is not at all a good example. Again, if we started with reality, I feel like the scaffolding is not as present. I mean, maybe, it may not be, but it's still not, like, reality is messy, right?
Just the last question. When you did the estimation,
Mhm.
when you used the Laban to estimate the model, for this model,
Mhm.
you deleted the function of standardized latent variable to get the
Yeah,
variance of the time.
Yeah, this is, remember in the example, I pulled out probably the wrong one. I realized this was a different metric for I had on this example, the means, I set the first item mean to 0, and then I estimated the factor mean. So it was one of those, in that part of the class we're talking about scale identification, I grabbed the wrong example. So
No, what I meant is that if you put like the function like the standardized
STD dot
LV, which is standardized latent variable.
That's right,
for
yeah.
all variables you have, it will, and if you put it true, it will
by default.
by default estimate the standardized the variance to 1 and the mean to 0.
Yes.
So you need to remove this if you want to do the marker indicator.
Yes, you do. Yes, if you want to do marker item,
To estimate the factor variance.
that's right.
Because it will estimate.
That's exactly right. That's right. That's exactly it. If you want to have the marker item technique to identify the factor variance, you cannot have the STD.LV equals true. Yes. Here, do you want to? I mean, I'm happy to talk more about this. I really want you to get these concepts. I think this modeling, the type of stuff that we do here will apply in IRT as well, although it's going to be harder to check fit. Well, for some of what we do. So I wanted to show you, see if I could come up with, here. I'm going to output the factor scores and show you that, and this is sort of on the fly, so this might give me something that's even harder to explain. But I'm going to try. Let's imagine I take my factor scores, A star scores, right here. These are my factor scores for each person for the situation with the two-factor model where I put negativity on. And let me see, I also had a model that was Model 01 estimates. I think Model 01, let me see this. Model 01 was just the single factor model. So let me just compare the factor scores for the two. Does that sound okay? I don't know why I'm asking you. I'm going to do this. So do you understand what I'm doing, right? I want to just kind of show the difference in two. Oh no, that's right. I have an error in my function. And was it one of you I sent this to? Mayumi? Was that who? I don't remember who I sent this to. Bishi, yes. Yeah, if you're running a one-factor model, my factor score reliability function may not work, and that's right. Anyway, I can't do it. Never mind. Actually, no, I can't.
So,
I'll just.
so can you do it for the method, for the two factors with the method with the second factor?
Yeah, I can. Hang on just a second here. I'm just. What was Levon's factor score function? It was. What was it? Predict? That's right. Thank you. There's the factor score. So if I do that. So if I do plot A star scores 1 with B, what do I get? There we go. Here's the correlation. This is the factor score for the model that had the negativity pulled out.
So which is the cutoff?
That's right. What's that?
Number 1 is the cutoff.
Number 1 is the cutoff, yep. And then this is the factor scores for the model with negativity, where everything's one factor. Now again, the factor scores for this model, you have to think the model didn't fit well, so you sort of have to not really believe those because something's going on. But you take a look. This is not just, they're not just summing to 1, or they're not just adding to a number variable. They're clearly correlated because the trait themselves, this is still the same trait. The only thing is that the situational, the negativity is now removed. And you think of the difference of the score. Someone here, this person on the original model had close to 0 for their score, but for the second model was down, past 1 standard, almost 2 standard deviations low for it when we control for that. Similarly, if I compare, I think it's this one. This is the negativity factor on the right here on the x-axis, and your original score scale on the y-axis. And then finally, if I wanted to compare this is the plot of the situational forgiveness and negativity factor from the two-factor model, not a bifactor. And you'll note that the trend is less obvious, but that's because we estimated them to be separate from each other, uncorrelated, right? So anyway, just saying they're not the same thing is what I'm going with. Right? It's a different
it's kind of like when
These lines right here are because the scale has a ceiling and a floor.
yeah, but could we say like because like the method factor, the value of the method factor increased, the value of the first factor will increase because or it's
Not entirely. No, it's just. I mean, there's no clear trend here. I mean, it sort of looks negative, like a negative relationship. But if you look where the bulk, that we're sort of being influenced by the ceiling and floor. The bulk of the points are right here in the center, and there, to me, that's mostly uncorrelated. And there's a few people at the ceiling and floor where it shifted them. So that's sort of what I get to.
You chose 3 because the positive 3 and positive 3 and negative, right?
No, this is just the range of the scores, how they came out. So
Oh.
so A star scores. If I do this. This is when I create the factor scores with that function I created, I put the standard error for each there, right? And so I had the first column was situation, it was the factor, second was standard error, so that's why I picked the first and third columns.
Okay.
Yeah. Okay. How we doing? Okay. Other thoughts or questions?
Thank you for going over all of
Oh, I'm happy to. This is I feel like this is the most relevant to your work. I mean, I want you to gain practical knowledge out of this class. I'm willing to sacrifice. Like the way I'm going to catch up with a lot of things on our syllabus is I'm going to tell you a little bit about IRT and tell you a little bit about the models of IRT that are most relevant. But Levon does not do anything close to what M+ will do, and since I don't want you buying M+, we're only going to focus mainly on what Levon does. And I'll say, if you want to know more about the M+ stuff, if you have different types of data, take a look at these slides. There's examples, there's things you can find, but they're all on M+ for that reason. So I think I'm going to use that time to shorten to kind of catch up. But so for that reason, I'd rather teach this well because it's still going to apply with us. So that's my rationale. Yeah.
Actually, related to that note, though,
Mhm.
just in the very beginning of our write-up for our homework, when we say what program we use,
Yeah.
we're going to say we use R.
R and the Levon package.
Right, okay.
And actually, if you want to cite it,
Isn't
and that
there something called M+ in what we're typing into R, though?
not
Mimic?
mimic
Yeah,
equals M+.
and so I was
Yeah.
like, all right, maybe I just say I'm doing M+.
No, actually, no. You have to say the software that you used. The cool thing about this, if you're in R, you can figure out how to cite the
I
package.
found that online last night.
If you type the function name citation and you put Levon, Lavaan, it will give you the citation to what the author of the package wants you to use to cite. And then the second, if you use LaTeX, I don't know if anybody but me does. This is just the bibliographic entry for it, which is how it works. What's that? Sorry.
We had someone who was obsessed with LaTeX
No.
in our regression class. Poor guy.
I'm not. You know what? I was like that in grad school, and then I saw the light. I was like, I don't want to compile all of my documents, and so I found the happy medium is Markdown, but I don't need to get you into that right now. So.
We'll give your information to him.
Yeah, no, I'm the guy who shows up at my whenever we meet up, my grad school colleagues and I all meet up at conferences and stuff. They'll have their slides in LaTeX and whatever else, and I'll be like, no, I used to do PowerPoint until now I'm fully promoted. I'm kind of like, well, okay, I'll get back into a little bit more code for us. Now it's HTML5, but so I make them go, oh, what's that? But it's all Markdown, so it's not.
I think we're fancy if we do Prezi.
Prezi's cool. I think that's cool. I do. I agree. I like the HTML. So I like, actually, the reason I do like this, anyway, never mind. I'll stop. Yes. Too much. Anyway, if you want to cite, so normally when I say I use the R package, and actually I use just the citation function, without anything in it, it tells you how to cite R. So this is what you do to cite R right here. And then I go and I say I use the LaTeX package, or is it Levon package, not LaTeX. And it's
Do I have to
citation.
cite every package you use?
I do. And the reason for that is, here in my field, we're often told that there's a thing in science that we talk about, which is our impact factor for all of our articles.
Yes.
All right, so here, let me go to my Google Scholar. You're going to see I'm not exactly great. And there's my old picture, God, long time ago. So it's not like I'm, all that well known or whatever else. I'm not really happy or not, but I don't really care to show you that. The big deal is you start to look at these types of articles and you don't get a lot of citations because when was the last time you cited like Cronbach for alpha? When was the last time you cited, anything? So all the things we do in methods, we're sort of at a disadvantage because you never cite the source that actually said, I use a CFA model. Did you cite yours, COG 67? No, of course not, right? And so what does that do? That means all of our impact factors for most of our journals are somewhere way lower than all the other journals that have a lot more people in their field. So you have the opportunity to cite the package you use, please do. Because it passes credit on to those who created it. It also passes credit on to the people who in our field. So sorry, as a methodologist, we need that.
So this is kind of like an in the weeds question on citations though, but like at least for us, like we use APA, and I know that like that had a URL in it, but we typically wouldn't include a URL in those citations. Would we include it anyway? Because
no, I wouldn't. I take the URL out. They're actually this is an old citation that hasn't been updated. Some of the newer packages have the DOI number that you'd want to put for API.
Yeah.
So you have to find it for this, but most, like I was just citing.
so you can't tell like what type you want, like AP or MLA or anything.
No, it just gives you the pure citation that they want you to talk about. And so the thing about R is this. So these DOI numbers are great because have you heard of DOI?
Digital objects.
Yeah. So what happens is you can go and figure out who cited it, right? And actually in people, it's one of the issues we're dealing with in our journal is how open we want for data. We want people to share their data more, but there's a lot of hesitation because ultimately, I don't get credit for it. Well, there are places that now give you a DOI number for your data sets. So you can cite data sets and you can talk about how much impact that data has had on the field and so forth. So it tries to provide it. And the same thing goes with this. Our packages themselves don't have the DOI number, even though that if we're using this for science and people have vetted most of the packages, that's a big deal. What people who write our packages, they often publish in this Journal of Statistical Software, which does give them the DOI. So I would look up where they want you to cite and find the DOI if you can do that and replace the URL with the DOI.
Okay, great. Thank you.
Yeah, no problem. And sorry I've had these conversations. I've this year, because I've been in more administration than I've ever been in my life before, I've had these conversations about methodologists and so forth. So I'm on a search committee for the psych department, and where they're looking for someone. They've lost a lot of quantitative psychologists. And that was my home department when I started here a long time ago. So I actually like my colleagues there quite a bit. And so I'm trying to help. And they were told by their dean that they would not be hiring a person who was trained in quantitative psychology as a field because they didn't want a quote unquote statistical consultant. They don't publish as much and they don't, blah, blah, blah. And then we could just hire them or whatever. That's what I've heard the story as. They want it, and the other story I've heard is, they also have a lot of holes in other places, so they're trying to be able to find someone who's in a field of psychology that also has some advanced methods that they want too. Well, part of the issue that always pops up with this is, take a look at the impact factors of their journals. It's all small, so we get shut down as a field because nobody cites the methods they're using. So if you're in that spot, just think about that going forward. It never hurts to cite more things than not. It's the same way I feel about like adding co-authors on a paper. Once you have a co-author, it doesn't hurt to add 5. So it just never. These are the things that are sort of easy that are able to be done. So be inclusive. I would encourage you to think about being. You can be however you like, but just for our field's sake, it really helps when you do cite R, or when you do cite that, because there's a lot of people who spend a lot of time on this. And to our university, we don't know how to evaluate this. If this person was a colleague of ours, and let's imagine they were an assistant professor, because they're not. They're probably actually. I think they're a little higher up than that. But if you were an assistant professor and they were spending their time on this, and all of us are using that, like just in this room, using their work, and the university says, yeah, but that's not a contribution.
So there's no way to know how many times the package has been downloaded?
There are package downloads, but they're not as directly tied to citations, right? Because a lot of people, or like our high performance computing center might just download all of them just to not have to, when install and so forth. So
So So like we use psych too.
Yeah,
I should psych
definitely,
too.
definitely.
Oh, that's great.
Yeah, so I'm just trying to give you things that no one ever talks about, but just
Yeah, nobody.
from our method, it helps us play the academic game better. And I don't think it hurts you to cite the package you're using.
Okay.
You know,
Okay.
so and that's all. I don't mean to be rude about it. Every field seems to have. There's always, regardless of the field you're in, there's always somebody who you feel like is putting your field down. And in the psych department, the quantitative psychology as a discipline has really dwindled in the last 50 years. A lot of psych departments have gotten rid of their quant programs for a number of reasons, and so it's kind of depressing to see. But it does happen. Maybe you've heard that in your fields too, like people put down what you do or whatever else, but maybe not. Maybe you pick good ones. So. Okay. So yeah, we're almost to the end of class, but that's okay. We're back to it. Now I will ask you, do you remember where we left off?
IoT.
We started IRT. We were doing, let's just do a quick little refresher of where we were before. How's that sound? Yeah, where'd you go? Why am I not viewing this window? Where did it go? Oh no, I know why. I'm not actually connected. Here we go. There it is. Here we are. Okay. We started by talking about sort of the general big picture of what we have to do IRT, and it started with the idea that we're not going to change the model from the idea of the theory part, right? The theory is on one side, right? That's sort of why we build our items. That's the factor. That's what we're saying is describing the item behavior. What we're changing is the data side of the model, right? The data we're going to change the assumption that we have continuous data, which would give us this line right over here, to something that's, Jesse's not here, but bendy, right? A nonlinear function, basically to allow us to keep our model predictions in range. This also helps a lot of other places. And so when it does this, if we just pretend that we have normal linear data, oftentimes we tend to be overconfident in how much we know about the data. The reliability tends to look much higher than it really should, right? Because ultimately, in categorical data, if you have 1, 2, 3, 4, or 5, there's only 5 ways a person can respond to an item, right? But if you map that using CFA, you're basically saying there's infinitely many ways a person can respond to an item, right? So the CFA model necessarily is assuming that you can get like a 4.2, a 4.3, things that are in between there, which sort of allows it to say, yeah, hey, I know a lot more about what a person's doing, when really there's only 5 ways you can respond to an item that shuts down what you can know about a person from each item. What I'm getting at is a concept that we're going to come back to at the end, but each item is containing, we talked a little bit about this in CFA, but each item contains a bit of information about the factor. Right? And we can actually quantify what information means. We do that a little bit more in IRT. And we're going to see this for each of the items. In CFA, we never really talk about it, but we can quantify it as well. For an item that measures one trait, it's the factor loading squared divided by the unique variance. That's how much information it goes. But you'll note that's a constant. Each item provides the same amount. And so in CFA, what you'd say is that you have this constant amount of information for an item. But when you switch to IRT, which is probably more appropriate when you actually treat the data as categorical, that information is actually going to shrink. And it's not only going to shrink, it's not going to be constant anymore. Some parts of the item will have much more information in certain locations of the trait than in others. But to get to items, remember logits? Now, how many have you had talked about logits before this class? None. Okay, 1. For those of you who haven't, I was there. I was you when I took Rod McDonald's class, and I will tell you that and actually Lisa and I have these shared stories. So she took Susan Embertson's class here years and years ago when Susan was here, and I took Rod, and both of those are like sort of my idols in the field. And when we both got to it, we're like, what the heck is a logit, right? So what I want to impart on you is we'll use the rest of the day today reminding us what a logit is, and then we'll have a weekend break and we'll come back and probably talk about it again. But remember, because what we're doing in a model is we're predicting the mean response. And if you have an item that's two values, a 0 and a 1, the mean of that has to be between 0 and 1. A probability is really what it is. And the logit takes the odds, right? The odds would be the probability divided by 1 minus the probability. And I did say the odds of what KU beating Iowa State was 0.1. Yeah, not a good chance. So the odds, though, is bounded below by 0, so we need to transform that into something that's... The goal in every one of these types of models that we're going to get to is that we want to predict the mean. We want to take the mean of the data and make sure it maps onto the whole number line from negative infinity to positive infinity. That's the whole goal in all of everything that we're doing, right? So a logit is the natural log of the probability divided by 1 minus the probability. Right? It's not the data, which is the hard thing to understand. If you try to take a logit of your data, it will break because the data are either 0 or 1. And if you put a 0 in, you get a 0 divided by 1, which is a 0 for the odds, and the log of 0 is undefined. And if you put a 1 in, you get a 1 divided by a 1, or 1 divided by a 0, which will break it. So it's not the data we're transforming, it's the mean, it's the predicted response itself. So you remember when I pulled up the predicted responses, we had that graph? That is what we would expect if we were to give a person an item hundreds of times and have them forget the item, what it means. The mean of the distribution of responses would be on that line. And so what the logit is doing is taking that predicted response, a mean, and converting it into a scale that would be predictable by the values that we have in our model. And actually, we're going to take the logit. Where we go here? We're going to go take the logit and use it to make our prediction on. And then if we want to go back to probability, we can just take the unlogit, the inverse logit. Right? And so when we talk about that, the logit is called a link function. This is a generalized linear models thing. So same thing happens in logistic regression. Then there's an inverse link function. So logit goes from scale of data to real number line, and the inverse goes from real number line to scale of data. So in factor analysis, when we had do this. In factor analysis, we were saying that the data was equal to a predicted response was for an item and a person. Right? It was this. It was the actual. This is a sort of this is essentially our mean. Right? So this should be on the scale of the real number line. Right? So it goes from negative infinity to positive infinity. So if we wanted to convert that to the scale of the data, what did we do to it? Nothing. Right? So in factor analysis, what we did was we took the inverse link function was the number 1. It's called the identity link. And the identity link, so basically if we took the number 1 and multiplied it by our mean, we'd get our data back because it's already on the same scale because of the assumption that the data are continuous. Right? If the data are continuous, if that assumption holds, then we don't need to do any conversion to it. However, if our data are 0s and 1s, we gotta take the mean. We predict the mean over here on a logit link. And we transform the mean to predict it. But then if we want to put it back as a probability, we just take the inverse of that. Now my pen won't work, so whatever. So, does that make sense? I feel like the tone in the room has gotten much more negative.
Actually,
It's warm in here, I know, and I'm sweating a lot talking about a hard topic.
Okay, so when you say the mean, like the probability, like that's fitting, like let's say we have a response 0 and 1, and the odd of that response would be like the probability of correct response divided by 1 minus the probability of getting a response with the left would be like the incorrect response.
That's right.
So the division will give us the mean for that item.
That's right. That's right, for a person.
For a person. Okay.
That's right. So what you have to think about is, on average, the person average, right? So it comes from what we have, the parameters of the item. So in factor analysis, it was the intercept for the item and the factor loading, and then what a person's factor score might be. And that gives us our predicted response for a person. Right? So
for each item,
For
there
each
will be an item for each individual.
It's a tough thing to conceive.
So to make it like, so the S shape of the response, like
Bendy.
the
Here.
bendy line, would be not for one person, would be for all.
That's right.
So the average would be
Hold
the
on.
point of all.
Hold on a second here. So what we're doing in every model is we're trying to predict the average, right? Whether or not we have, it's real easy to think about in ANOVA, right? Because we have one group, we have another, we calculate the means, that's it. Well, we're doing the same thing in regression, but we're assuming the average is now conditional on a predictor. And not only conditional on a predictor, it's on a line, right? So every point on that line is the average, conditional on the predictor. We're going to do this, and so again, the data, each one person, we may only have one observation of a given value, but because we're mapping that line to everything, well, we're doing the same thing, but we're doing it on a different scale.
As the y hat.
That's right, y-hat, that's right. So if you think of it this way, where this is coming from, this may be a little overly technical, but I'm going to try, all right? So there's this thing called the Bernoulli distribution, all right? So this is the probability that a y equals a 1, and it is given, what the heck just happened? Okay, this is equal to, essentially right here, go away. This is for an item in person again, to the y, the item in person, times 1 minus pi, 1 minus y. Now what is pi? This thing right here is, pardon me, this is the probability that y equals some value, 1, 0, or 1, right? This is sort of what value it happens to be. This pi right here, pi, is actually the probability that y equals 1. We're going to define it as that, right, for our model. Right? And so that's the mean. And so the mean of the Bernoulli distribution is given by, so if you want to know in the long run, if you have a bunch of data, what's the mean of this distribution? It's given by pi. It's literally that's the probability. If you take a look at, if we have an empty model, if we just fit an intercept to this, right, the mean of it would be given by the proportion of people with a 1, right? So, but this mean, this thing right here only goes between 1 and 0. That's the range of this probability, right? So to really do our linear model predicting for it, we need to stretch this to be positive infinity to negative infinity. So what we're doing statistically for each analysis is we're saying, okay, we're going to first take the logit of pi for this item in person, and really that's going to be the natural log of pi, item in person, over 1 minus pi. Now that term itself goes between negative infinity and positive infinity, but that's where we're going to put our model. So let's just make this a really simple model. We're just going to have an intercept for it. This is a logistic regression. There's no factor involved at all. It's just logistic regression, right? So if we go and estimate this model, we know what the mean is. We can calculate the mean by hand, but to convert that mean, let's say the mean is 0.5, right? Right? We could see that. Well, that really what we're doing in the computer is we're basically trying out values of beta 0, which are between negative infinity and positive infinity. And then we go and back translate it, right? We take beta 0, and this probability, if we take e to beta 0 over 1 plus e beta 0, we get the probability back, right? So we take beta 0, we plug it into this function, we figure out the probability, and then we go put it in this likelihood function to figure out which beta 0 gives us the most likelihood. So this is for one person, but we take the product of that across all the people and we get a likelihood, maximum likelihood estimate, right? That's how the likelihood sort of works. So ultimately, we don't change their data. We're just going to make we're going to plug our parameters into this kind of conversion process to sort of put them into the likelihood so that they stay in bounds. Now, what does this look like for a factor analysis, right? If instead of calling it beta 0, if we took this and called it, this logit was now mu for the item plus lambda for the item times f for the person, right? So let's keep thinking this. Let's imagine mu was 0 and lambda, let's call it 1, just make it easy. And let's take a person with a factor score of, I don't know, 2, right? Right? So this logit now gives us a value of 0 plus 1 times 2, a value of 2. So we would say this is our predicted log odds of a value of 1 for that person. So what does that mean for the probability they answered with 1? Well, again, we back translate it. We put 2 into this e to the 2 over 1 plus e to the 2. And if we go back to my... All right, fine, don't do it that way. We go back to the slide over here that has logits on it. We'll see that a value of, well, 2.2 gives us a probability of 0.9. Right? So now we're going to say, oh, that person has a 90% chance, or a little close to a 90% chance of answering this item right. So what we've basically done is said, what we're doing is factor analysis, but on logits. That's how we're doing it. Does that make sense? Is that weird?
Yeah. Kind of like.
I took goodwill and threw it away, didn't I? I can see the looks. I can see it. Logits are crazy, right? Because they don't exist.
Yeah, it's hard to like grasp. You know, it's very abstract.
It is. So what's happening in the computer is effectively this. It's for each person, it's trying a bunch of factor scores. Right? It's saying, okay, are you here? Are you here? Are you here? Are you here? And every factor score it tries, it changes their own personal logit, and that changes the value of the probability.
How is that related to the maximum likelihood estimation?
Well, we'll get there. I'll leave that. If we really want to keep this fine, we're not going to talk about that. But what I want to talk about is this. We want to be nice. There's a ton of link functions out there for each types of data. Logit is one, and we talked about this before. Remember the other one? Probit, which was the inverse normal distribution, right? So the same thing happens instead of taking the log of the odds. Now we're going to take that probability and convert it to a z-score, right? Using the cumulative normal distribution, right? And so we predict the z-score, and we back convert it into a probability, figuring out the inverse of that, right? Yeah, question? No?
Sorry.
No, this is not good, is it?
Okay. No, it helped. I understood things best so far when I did like this third homework because it all finally connected to me. So
Yeah, hang on to that.
reason why, yeah.
Actually, you know what's cool about that is, and I'm really happy you said that. I know I need to let you go, but let me just say this. If you're okay with just that ambiguity for a second, right? Because what's going to end up happening is it's going to start to look like a lot like factor analysis. We're going to have an item intercept. We're going to have a slope, a factor loading. It's going to look the same almost, but instead of dealing with data that we're going to have a few more terms when it comes actually to intercept. But now it's making these other predictions. So we're going to get there. You're going to have a chance to practice that. I'll let you go now. If you have questions, though, stick around. Ask me after class. So, thanks everybody. Have a good weekend. I will have office hours tomorrow, 9 to 11, in the Watson Library. So come find me. All right.
I'm sorry.
Just a second.